2002 National Electrical Code introduced a revised approach to determining the ampacity of conductors serving air conditioning and heating equipment. This update centers around the application of a 100% demand factor for both air conditioning and heating loads, irrespective of whether the installation is primarily for cooling or heating. In contrast, the 1999 National Electrical Code employed a different methodology. It stipulated a 125% demand factor for air conditioning loads and a 100% demand factor for heating loads. This meant that the calculated ampacity of conductors intended for air conditioning had to be increased by 25% to accommodate the perceived higher demand associated with such systems. The shift to a uniform 100% demand factor in the 2002 National Electrical Code stemmed from empirical research and field data analysis. These studies indicated that the actual electrical demand exhibited by air conditioning systems under typical operating conditions is often lower than the previously assumed 125%. Consequently, the National Electrical Code revised the calculation method to more accurately reflect real-world usage patterns. This modification offers several key benefits. Firstly, it streamlines the process of calculating conductor ampacity for both air conditioning and heating systems, making it more straightforward and less prone to errors. Secondly, it enhances the consistency between the calculated conductor size and the actual electrical demand imposed by these types of loads, contributing to more efficient and cost-effective electrical installations. It is important to understand the implications of this change for electrical design and installation practices. When working with the 2002 National Electrical Code or subsequent editions, the 100% demand factor should be applied to both air conditioning and heating loads. This differs from the approach outlined in the 1999 National Electrical Code, where a 125% demand factor was used for air conditioning loads. The proper application of the demand factors is crucial for ensuring that conductors are adequately sized to handle the intended load without being unnecessarily oversized. Oversizing conductors can lead to increased material costs and may not provide any significant performance benefits. To accurately determine the conductor ampacity, several factors must be considered. Firstly, the rated current of the air conditioning or heating equipment must be obtained from the manufacturer's nameplate. This information provides the baseline current draw of the equipment under normal operating conditions. Secondly, any applicable correction factors or adjustment factors must be applied to account for ambient temperature, conductor bundling, or other factors that may affect the conductor's ability to dissipate heat. Thirdly, the calculated ampacity must be compared to the ampacity ratings listed in National Electrical Code Table 310.15b16 to select the appropriate conductor size. This table provides ampacity ratings for various conductor types and sizes based on their insulation temperature rating and installation conditions. When performing these calculations, it is essential to consult the specific requirements outlined in the National Electrical Code for air conditioning and heating equipment. The National Electrical Code provides detailed guidance on the installation and wiring of these types of loads, including requirements for overcurrent protection, grounding, and disconnecting means. It is also important to consider any local amendments or interpretations of the National Electrical Code that may be in effect in the jurisdiction where the installation is being performed. Local authorities may have specific requirements that differ from the National Code, and it is the responsibility of the installer to comply with all applicable regulations. In summary, the change in the National Electrical Code to a 100% demand factor for both air conditioning and heating loads reflects a more accurate understanding of the actual electrical demand of these systems. This change simplifies the calculation process and promotes more efficient and cost-effective electrical installations. The electrical professionals should familiarize themselves with the current National Electrical Code requirements and apply them correctly to ensure safe and compliant installations. The demand factor is a critical concept in electrical load calculations. It represents the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system, or the part of the system under consideration. The demand factor is always less than or equal to 1. The 100% demand factor for both air conditioning and heating loads in the 2002 National Electrical Code means that the calculated load is equal to the total connected load of the equipment. In other words, the electrical system must be capable of supplying the full rated current of the air conditioning or heating equipment at all times. This is a conservative approach that ensures the system has sufficient capacity to handle the load. The previous method, which used 125% demand factor for air conditioning loads, was based on the assumption that air conditioning equipment would typically operate at or near its full rated capacity for extended periods of time. However, research and field data have shown that this is not always the case. In many situations, air conditioning equipment operates at less than its full rated capacity, especially during periods of mild weather or when the building is not fully occupied. Therefore, the 2002 National Electrical Code revised the demand factor to better reflect the actual operating characteristics of air conditioning equipment. The change in the demand factor does not mean that the electrical system can be undersized. It is still essential to select conductors and overcurrent protection devices that are adequately sized to handle the load. However, the 100% demand factor allows for a more accurate calculation of the load, which can result in more efficient and cost-effective electrical installations. It is also important to note that the National Electrical Code provides specific requirements for calculating the load of air conditioning and heating equipment. These requirements are outlined in Article 220 of the National Electrical Code, which covers branch circuit, feeder, and service calculations. Article 220 provides detailed guidance on how to determine the connected load of various types of equipment, including air conditioning and heating systems. It also provides information on how to apply demand factors and other adjustment factors to calculate the total load on the electrical system. When calculating the load of air conditioning and heating equipment, it is important to consider all of the relevant factors, including the rated current of the equipment, the operating voltage, and any applicable correction or adjustment factors. It is also important to consult the specific requirements of the National Electrical Code to ensure that the calculations are performed correctly. Failure to properly calculate the load can result in undersized conductors or overcurrent protection devices, which can create a safety hazard. In addition to the changes in the demand factor for air conditioning and heating loads, the 2002 National Electrical Code also introduced other changes related to the installation and wiring of these types of equipment. These changes included revisions to the requirements for overcurrent protection, grounding, and disconnecting means. It is important for electrical professionals to stay up to date on the latest changes to the National Electrical Code to ensure that they are performing safe and compliant installations. The National Electrical Code is updated every 3 years, and each new edition includes revisions and updates to the existing requirements. Electrical professionals can stay informed about these changes by attending training courses, reading industry publications, and consulting with experts in the field. By staying informed and following the proper procedures, electrical professionals can help to ensure the safety and reliability of electrical systems. Furthermore, the correct application of a 100% demand factor, according to the 2002 National Electrical Code, requires a thorough understanding of the equipment's nameplate data. This nameplate provides crucial information such as the rated voltage, current, and power consumption, which are essential for accurate load calculations. Ignoring this information can lead to significant errors and potentially unsafe installations. Consider a scenario where an air conditioning unit has a nameplate rating of 20 amps at 240 volts. Using the 2002 National Electrical Code, the calculated load would be 20 amps. This value is then used to select the appropriate conductor size and overcurrent protection device. If the 1999 National Electrical Code method were used incorrectly, the calculated load would be 25 amps 20 amps x 1.25. This could lead to the selection of larger conductors and a higher rated overcurrent protection device than necessary, increasing material costs without improving safety or performance. It is also important to understand the difference between demand factor and diversity factor. While both factors are used in load calculations, they represent different concepts. Demand factor, as discussed, is the ratio of the maximum demand to the total connected load. Diversity factor, on the other hand, is the ratio of the sum of the individual maximum demands of a group of loads to the maximum demand of the entire group. Diversity factor is typically used in feeder and service calculations to account for the fact that not all loads will be operating at their maximum demand simultaneously. The National Electrical Code provides guidance on the application of diversity factors for various types of loads. For example, National Electrical Code Table 220.42 allows for a diversity factor to be applied to the general lighting load in a dwelling unit. Similarly, National Electrical Code Table 220.44 allows for a diversity factor to be applied to the receptacle load in a dwelling unit. When applying diversity factors, it is important to consider the specific characteristics of the loads being served and the likelihood that they will be operating simultaneously. The National Electrical Code provides guidance on the appropriate diversity factors to use in various situations, but it is ultimately the responsibility of the electrical designer to determine the appropriate factors based on their knowledge of the specific installation. In conclusion, the transition to 100% demand factor for both air conditioning and heating loads in the 2002 National Electrical Code represents a significant shift in electrical load calculation practices. This change, driven by empirical data and a desire for greater accuracy, has simplified the calculation process and promoted more efficient electrical installations. Electrical professionals must understand the implications of this change and apply the current National Electrical Code requirements correctly to ensure safe, compliant, and cost-effective electrical systems. The proper selection of conductors and overcurrent protection devices is crucial for the safe and reliable operation of electrical systems. It is essential to follow the National Electrical Code requirements and to consult with qualified professionals when necessary. The change to the 100% demand factor is just one example of the many ways in which the National Electrical Code is constantly evolving to improve electrical safety and efficiency. By staying informed and following the latest code requirements, electrical professionals can help to ensure that electrical systems are designed and installed to the highest standards. This ultimately benefits everyone by reducing the risk of electrical hazards and promoting the responsible use of energy.